We will go on to some problems here about mixtures of ideal gases. So, it says a cylinder contains 70 grams of oxygen and 300 grams of helium. So, I have oxygen which is 70 gram. Let me convert that into kg. I have helium which is 300 gram. The volume of the cylinder is given as 10 liters. That is 10 into 10 power minus 3 meter cube. So, 1 liter is of course 1000 cc. A centimeter is 0.01 meter. So, therefore, 1000 liters is 1 meter cube. So, we see that we have this conversion here. We are asked to calculate the partial pressure and volume of each gas. So, we want the partial pressure of oxygen. We also want the volumes of each gas and the total pressure in the cylinder at 25 degrees centigrade. So, the temperature is 25 degrees centigrade. Whenever we deal with ideal gases, we are often going to use the ideal gas law. So, it is useful to convert these into the Kelvin scale. So, this is 273 plus 25, 273.15 if we want to be very exact, but we will just use 273 for the time being. So, we get this as 298 Kelvin. So, we have this information. So, the total volume of the cylinder is given. I know the mass of each of the components. What I can do is I can find out the mass fractions of each of the components. So, I am going to use the alphabet Y to denote the mass fraction. So, mass fraction of O2 is mass of O2 divided by total mass. The total mass, there are only two components here. So, it is essentially mass of O2 plus mass of helium. Which is essentially .18. The mass fraction of course does not have any units. Then I can find out the mass of helium, mass fraction of helium in the same fashion. It would be the mass of helium divided by mass of O2 plus mass of helium. But since mass fractions are defined like this, we also know that sum of all the mass fractions should be 1, and I have already got this as 0.18. So, I can also write this as 1 minus mass fraction of O2, which gives me 0.82. We can also do it the other way, we will get the same answer, because the definition is such that whenever you sum all the mass fractions, they should be 1. Therefore, we get the mass fraction of helium as this. What we would like to find out is the partial pressures. So, if we use the Dalton's law of partial pressures, what we see is that the partial pressure of oxygen, for example, is the mole fraction of oxygen into the total pressure. Similarly, the partial pressure of helium is the mole fraction of helium into the total pressure. So, what we need is the mole fractions of these species. In order to find out the mole fractions, what we can do is find out the molecular weight and then find out mole fractions. So, that is something which we can do. The molecular weight of the mixture we need to find. So, molecular weight of each of the components, molecular weight of oxygen is essentially 32 kg per kilomole. So, the molecular weight of helium is 4 kg per kilomole. So, we had, for finding out the molecular weight of a mixture, we said this is essentially 1 by sigma of mass fractions divided by the molecular weights. So, I have 1 by, so for oxygen I had Yi as 0.18 divided by 32, plus for helium I had 0.82 divided by 4. Of course, I can expand this as 1 as YO2 by molecular weight of O2 plus Y helium divided by molecular weight of helium, which gives me this. So, I can now find out the values of this, which gives me a total molecular weight of 4.74 kg per kilomole. This value of course should be somewhere in between these two, since this contains mostly helium. This value is closer to the value of helium, that part of it which is clear. So, what I am looking for is to find out the mole fractions. So, what we can see is, so we have the mole fraction of the ith species is essentially Yi by the molecular weight of I into the molecular weight of the mixture. So, we have for oxygen Yi is 0.18 divided by 32, and for helium we have 0.82 by 4 into this, which is essentially so if we sum up these two, they should also sum up to 1. So, instead of finding out this, we could have also taken 1 minus this for the other value or for any of those. So, what we see is that when you look at mass fractions, there is about 18% of oxygen and about 82% of helium in terms of mass. In terms of moles or in terms of say volume, what we see is that helium has a larger number. This is true because oxygen is a much heavier molecule. So, if I have like 1 kg of oxygen and 1 kg of helium, I would expect a larger volume for the helium because it is a lighter molecule, and I would expect a smaller volume for the oxygen. So, if I look at mole fractions, which is essentially looking at number of moles or number of or the volume, I would expect that the mole fraction of helium would be larger than the mass fraction of helium in these kind of cases. So, we have these. What we were looking for is the partial pressures. So, what we knew is that the total volume is 10 liters and the total mass is 0.37 kg. So, total mass is this, total volume is I think it is a 10 liters. So, what we know is also that the temperature is 298 Kelvin. For finding out the partial volumes is easy enough because from Amagat's law we see that if we just multiply the volume by this, we would get the partial volume, assuming that both of them are the same pressure. If the volume fraction is also the mole fraction. So, the partial volume would be the total volume into this, and the volume of helium would be so as far as volumes go, we have them directly. What we are also asked to find out is the partial pressures. So, we know that the partial pressures also from Dalton's law of partial pressure will be in this fractions. What we do not know is the total pressure. So, we need to find out the total pressure. We can assume both of these to be ideal gases and for the mixture also to be ideal gases. Then for the mixture, what we can write is pressure of the mixture into volume of the mixture equal to mass of the mixture into R of the mixture into temperature of the mixture. So, we know the temperature, that is 298, we know the mass, which is 0.37 kg. The specific gas constant of the mixture is the universal gas constant divided by molecular weight of the mixture. Sorry about that. So, this is 8314.5 joule per kg Kelvin divided by molecular weight of the mixture, which is 4.74 kg per kilomole. And if I take this volume to the other side, I divide by 10 in 10 power minus 3, and that would give me the pressure of the mixture. I can find this out. So, that comes out about 193 bar. If I do this, so it comes out to 193 in 10 power 5 or 19 in 10 power 6. So, I can also write as 19 megapascal. And now I can find out the individual pressures. So, partial pressure of O2 is XO2 into this total pressure. So, that is this value into 0.026, which gives me a value of about 5 bar, and partial pressure of helium is X helium into the total pressure, which is 187.2 bar. Of course, with a lot of these problems, we can also do this in different ways. I need not have, for example, found out the molecular weight of the mixture or in R of the mixture. What I could have done is pressure of oxygen into volume of oxygen is m into R into T. That would also work because the temperature of oxygen is known. I know the mass of oxygen. I could have done it in that way as well. So, I can do it in different ways. It does not matter. So, these are the values which I get for this problem.